So now, you know, let's consider the change of basis view. So g of x, now what I'd like to do is I'd like to write it as you know, some linear combination of these new basis functions that I developed, these new basis vectors that I developed, right. So remember we looked at the standard representation, and now this is the Fourier representation. So I did not yet tell you what these coefficients are, but you know, as long as it's a basis, obviously the definition of basis is that these coefficients will exist, right. So we have to compute them. So that's going to be our next step. So what are these coefficients? So we claim that g hat of sigma is Ex chi sigma x gx. We will prove this. So here x is uniform. So we've so far we've sort of simply proved the fact that it's a basis, and we've written it as written any function as a linear combination, and now we need to work out what are these coefficients. So you know, we'll do that. There is nothing very sophisticated. Let's prove this claim. So Ex chi sigma x gx is, you know, Ex. So now let's write, let's sort of open up gx, okay. So what is gx? We said it's, you know, g hat gamma summation g hat gamma chi gamma x, right. So this is just following from here, right. So I'm just writing gx using this notation here, and there is this extra term here. So there will also be a chi sigma x over here. Okay, I hope that this was clear. We did nothing. Okay, we're just sort of doing some simple symbolic pushing around. So we simply replaced gx using this expansion. Okay, so now this is equal to what? So this is, you know, summation over gamma g hat of gamma Ex of chi sigma x chi gamma x. And what is this going to be? This is going to simply be g hat of sigma, because of what we just proved, right. So when gamma is equal to sigma, then and then alone do we get a 1, right, and otherwise it's 0. So I proved the claim, right. And the special case of this is, you know, special case is g hat of 0, which is Ex chi 0x gx, right, which is nothing but Ex gx, right. So this is this also helps us to get a little bit of intuition about what's going on, right. So the expected value of gx is g hat 0. So, it is the coefficient for it's the coefficient for the 0th term in the sum. Okay, great. So, let us keep going. So, now that we have defined the Fourier basis, let us connect it to the Hadamard transform. So, the main idea which I have been saying multiple times, but we will finally write down, is that this change of basis is going to be implemented by the Hadamard transform. Okay, so, implementation. Okay, so the claim here, implementation of basis change, right. So, the claim here is that if I consider any psi, right, which is some 1 over root n. So, here I am thinking of n as 2 to the n, capital N as 2 to the n, just to simplify notation a little bit. Okay, so, this is summation over x, sum g of x, then h of psi is this. It's this. So, it's the, so basically if I have psi in the standard basis representation, applying Hadamard to it gives me the Fourier basis representation, and this is kind of all the magic that's actually been going on. The fact that this is an exponential space, right, and you can efficiently compute this Hadamard transform, the quantum Hadamard transform. This changes the basis. Of course, we are not done because we cannot access this information. So, for that we need a measurement, and that is why there are some problems that work and some do not work, right, because there are a few problems where having done the change of basis, when I do the measurement I actually get something useful. This will not be true for everything. Okay. So, let us sort of quickly prove this. So, let me write this down. So, now obviously I can move the Hadamard inside, and you remember that while studying the algorithms we had worked out what is the Hadamard transform for a given quantum state. Okay. So, does anyone remember what it was? Yeah, summation over something, let us say gamma, minus 1 to the gamma x, right, gamma. So, this is going to be summation, maybe I will use a different color to illustrate it clearly. Okay. So, this we already saw that this is nothing but summation over gamma, okay, 1 over root n minus 1 to the gamma x gamma. This we already developed previously. So, we will not do it again, we will simply use it here, right. So, now using that what do I get? So, I get one over root n summation x g x, okay, summation gamma 1 over root n minus 1 to the gamma x gamma. Okay, so this is, I am just rewriting it. This becomes, you know, summation over gamma 1 over n, summation over x gx minus 1 to the gamma times x gamma. Okay. And this in turn can be written as summation over gamma, the expectation of x, right. So, g of x and chi gamma x. Does everyone agree? So, this is just the definition of chi and the definition of expectation. Everyone agrees with this? Just by definition. Okay. But now, you know, we are doing good because we already proved that this is g hat gamma, right. So, this is nothing but summation over gamma g hat gamma gamma, and this of course is what we wanted. Okay, so very quick recap, what did we do? We defined a new basis and we computed the coefficients. And yeah, these are the coefficients, right. So, where is it? Yeah, these are the coefficients. Okay, and then we claimed that you know, the basis change can simply be accomplished by applying the Hadamard. And you know, because we know that the Hadamard is its own inverse, one sort of quick corollary that follows is that I can actually get back my original state by applying the Hadamard to this new state. Okay. So, this we have also already seen, just a quick reminder. Okay, great. So, you know, we developed this machinery. Now, let us take a peek at some of the algorithms that we have already seen. Okay, so in particular, I will just spend a few minutes talking about the one of the first important algorithms we saw, which was the Deutsch-Jossa algorithm. So, let us look at that again. Okay, so here if you remember, we had this function f, and we had a promise that you know, either f is always 0 or f is balanced, right. We had this guarantee and we saw an algorithm and we also analyzed it. So, if you does anyone remember the algorithm? It was actually one of the cleanest examples of rotate, compute, rotate, right. So, we took 0 to the n, we applied hn to it, if you remember, then we applied the function. And which function? So, there are multiple ways of computing a function. We used the phase kickback idea, right. So, where you encode the function output in the phase, so in -1 to the fx, right. So, we applied that and then we you know, rotated again using Hadamard, and then we measured. So this was our algorithm. So maybe you know, I can, so yeah, so we had 0 which was applied to Hadamard, okay, which was then applied to this function oracle, the, you know, plus minus 1, so the phase kickback. And then, you know, we again had the Hadamard, and then we had measure. And when we measured, we observed the amplitude on the point 0, if you remember. Okay, so in one case you always got 0, in one case you never got 0, and this is how you learnt. You know, you learnt which of the two cases is true for the function. So now what we will see is that actually what is happening here is that this circuit is actually computing the Fourier transform for a particular function. So let's just write this down. So let g of x be, you know, minus 1 to the f of x. So remember what is f, okay. So f is given in our function description over here. And now we are defining a new function g of x. So you can convince yourselves that the output of the circuit is actually nothing but this. Okay, so first you get a superposition over x, then when you apply the oracle to it, then you get superposition over x with minus 1 to the f of x, right. And now minus 1 to the f of x I defined as g of x. So now when I apply the Hadamard again, I simply get the Fourier coefficients of that, because we said that the Hadamard implements the, so it is right. So this second Hadamard, so many of us are looking a bit lost. Okay, so maybe we can write this in a little bit more detail. Let me call this as psi 1, okay, and this as psi 2 and this as psi 3, let us say. So now what is happening? Let us consider psi 1. What is psi 1? Everyone agrees that this is a superposition over all inputs, right. So 1 over 2 to the n, actually square, sorry, not 2 to the capital N. So because, yeah, so and a square root. So it is this summation over all x, everyone agrees with this, right. Now I will apply the function. So what will I get? I will get 1 over root n, I am applying the oracle, right. So I will get summation over x minus 1 to the f of x, everyone agrees, everyone agrees. Now I am simply redefining this to be g of x, and now I will simply apply the Hadamard, right, to get this. That is all I was saying. So what is happening is that the circuit is actually computing the Fourier coefficients of this particular function minus 1 to the f of x. So now let us examine what happens, what is g hat 0. Remember what is you know, g hat of 0, so it is just Ex Gx, right. We saw this, okay. So now what is Ex Gx? Now Gx is minus 1 to the f of x. So this is Ex minus 1 to the f of x, okay. And now if f of x is always 0, then what happens? This is 1. If f of x is balanced, then what happens? This is 0. So you know, this G hat 0, it tells me which of the two cases is true, right. So, when I measure, I can figure out which of the two cases is true. So, basically converting it to the Fourier representation, right, allowed me to get to sort of isolate this pattern into this G hat 0. So, therefore, now when I measure, right, what happens with respect to the point 0 is sufficient to tell me whether the function was constant or balanced. All right. So, good. So, this was the Fourier transform over Z2. Now, what we'll do is we'll also see another very important algorithm called Grover's algorithm. So, this you know, this is one of the most famous quantum algorithms. It also makes use of the Fourier transform, and then we will move to like the generalized Fourier transform over Zn, and that will lead us to Shor's algorithm. So, hopefully by the end of next week we should have seen Shor's algorithm.